Assalamu alaikum, brothers and sisters. Welcome to the journey of Quest, where we quench your thirst of knowledge. Imagine a world where every step you take, every car that moves, and even the rain falling on the roof could power our cities. How could this be possible? Welcome to the fascinating realm of piezoelectric energy harvesting, a process that might sound like science fiction but is increasingly becoming a tangible part of our technological landscape. At its core, this technology converts mechanical stress, like walking, driving, or even raindrops hitting surfaces, into electrical energy. How does this work? It all starts with piezoelectric materials. These are unique substances that generate electricity when they are mechanically deformed. This deformation could be caused by pressure from footsteps on a pavement, tires rolling over a highway, or rain impacting a building's roof. The potential of piezoelectric energy harvesting is vast. It promises a future where the energy of everyday activities is harnessed to power streetlights, smartphones, and even entire grid systems, all without burning a single fossil fuel. Stay tuned as we uncover the magic behind piezoelectric materials and their role in a sustainable future. Ever wondered how pressing or bending certain materials can generate electricity? This remarkable phenomenon is called piezoelectricity, a word stemming from the Greek piezein, which means to squeeze or press. Today, let's unravel the science behind this fascinating effect and understand how it plays a pivotal role in energy harvesting. At the core of piezoelectricity lies the behavior of certain crystalline materials. These materials, when subjected to mechanical stress, such as pressing, twisting, or bending, undergo a significant transformation at a molecular level. Imagine a material's internal structure like a series of tiny springs and weights. When you apply force, these springs compress or stretch, changing the position of the weights. In piezoelectric materials, these weights are electric charges. This brings us to a crucial concept. The piezoelectric effect occurs due to the alignment and displacement of electrical charges within the material. When stress is applied, the symmetry within the crystal lattice of the material is disturbed, and this leads to an electrical polarization. Think of polarization as a shift from a state of no charge separation to a state where there is a clear segregation of positive and negative charges within the material, creating what we call electric dipoles. Each molecule or unit cell in the piezoelectric material forms an electric dipole. This is where the positive and negative charges are separated but confined within the same structure. When these dipoles align due to mechanical stress, they generate an electric field. The magnitude and direction of this field depend on the material's properties and the nature of the applied stress. By understanding these interactions, scientists and engineers can craft materials that convert mechanical energy into electrical energy with remarkable efficiency. This is not just about generating power but transforming how we interact with technology and the environment. With these basics in mind, let's delve into how this principle is harnessed in practical applications. Now, let's get technical and explore the equations that govern piezoelectric materials. At the heart of piezoelectricity lie certain key equations that describe how mechanical stress translates into electrical energy. The fundamental equation for the direct piezoelectric effect can be expressed as D equals sign D asterisk S. Here D represents the electric displacement field, which correlates with the amount of electrical charge generated. The symbol D stands for the piezoelectric coefficient, which is a measure of the material's ability to convert mechanical stress into electrical energy. Finally, S symbolizes the mechanical stress applied to the material. To put this into perspective, imagine applying a force to a piezoelectric crystal. This force induces a mechanical stress, S, in the crystal. The crystal's intrinsic properties, encapsulated in the piezoelectric coefficient D, then dictate how effectively this stress is converted into an electric displacement field, D. It's the generation of this field that leads to the production of electrical charge on the surfaces of the crystal. Conversely, the converse piezoelectric effect describes how an electric field can induce mechanical strain in a piezoelectric material. The equation for this effect is S equals sign D asterisk E, where E represents the electric field applied. This shows the material's ability to deform mechanically in response to an electric field, a principle that's crucial in applications like precision actuators in optical and acoustic devices. For a simple mathematical illustration, consider a piezoelectric material with a coefficient D of 200 picocoulombs per newton. When a stress of 100 newtons per square meter is applied, the electric displacement field generated is 200 picocoulombs per square meter. This conversion from mechanical energy to electrical energy is not just fascinating, it's the cornerstone of piezoelectric technology. Understanding these equations helps in designing more efficient piezoelectric devices. By delving into the specifics of how stress and electric fields interact within these materials, engineers and scientists can optimize piezoelectric devices for a myriad of applications. From energy harvesting in wearable technology to advanced sensors in aerospace. This understanding isn't just academic, it's a pathway to innovation and efficiency in the real world. How do we take the science of piezoelectricity from the lab to the streets? The journey from theoretical physics to practical application is as fascinating as it is vital. Let's delve into how piezoelectric materials are making their mark in the real world, transforming everyday energy into power sources. Imagine stepping onto a floor that harnesses your footsteps to generate electricity. This is not a scene from a futuristic movie, but a reality in places like train stations and malls where piezoelectric floor tiles are installed. These tiles capture the kinetic energy from the impact of people walking and convert it into electrical energy. This energy can light up signs, power advertisements, or even contribute to the building's overall power supply. Now, let's take this concept a step further with wearable technology. Smartwatches, fitness bands, and even clothing can integrate piezoelectric fibers. These fibers generate electricity from the normal movements of the human body. Every gesture, step, or turn becomes a source of power, keeping devices charged and collecting data without ever plugging them into a wall socket. The applications extend to the very infrastructure of our cities. Bridges and skyscrapers can be outfitted with piezoelectric sensors that monitor the health of the structure. These sensors can detect and measure vibrations, providing data that helps predict and prevent potential failures. This not only ensures safety but also enhances the longevity of the infrastructure. In the realm of transportation, piezoelectric technology finds its way into the roads we drive on. Certain highways are equipped with embedded piezoelectric materials that collect energy from the pressure of passing vehicles. This energy can then be used to power streetlights, traffic signals, or emergency road signs, contributing to a more sustainable urban environment. These applications are just the beginning. The potential extends far beyond what we currently see. As we continue to innovate and integrate piezoelectric materials into our daily lives, the boundary between science fiction and science fact becomes increasingly blurred, paving the way for a more sustainable and technologically advanced future. Every technology has its hurdles. What are the challenges faced by piezoelectric energy harvesting? Indeed, as promising as piezoelectric technology is, it's not without its challenges. One of the primary concerns is the durability of piezoelectric materials. These materials, often ceramics or crystals, can degrade under extensive stress or over long periods, limiting their lifespan and reliability in applications where consistent performance is critical. Efficiency also poses a significant challenge. The conversion rate of mechanical stress to electrical energy is not always optimal, which can be a deterrent in environments where maximizing energy output is crucial. This efficiency is often dictated by the properties of the materials used, as well as the precision of the engineering involved. Cost is another significant barrier. High-quality piezoelectric materials can be expensive to produce and process, making the technology less accessible for widespread use. Despite these obstacles, the scientific community is actively engaged in research to enhance the durability, efficiency, and cost-effectiveness of piezoelectric devices. Innovations in material science, such as the development of new composite materials and the improvement of fabrication techniques, are paving the way for more robust and economically viable solutions. Despite these challenges, the future of piezoelectric technology looks promising. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon, and stay curious for new uploads.